My name is Lucian Covarrubias, and I'll be presenting MiyagiBot, a robotic system capable of catching objects with a two-finger gripper. For anyone that's seen the hit movie Karate Kid in the 1980s, they'll probably remember the scene where Mr. Miyagi, the Karate Kid's teacher, is trying to catch a fly with his chopsticks. Now, the precision and speed required to accomplish this task is part of what inspired this project, but instead of using chopsticks, we're actually just going to be using a two-finger gripper because many of the same properties still apply. For the simulation setup, there's three main components. The first of all, obviously, is the robot, and for this case, I used the KUKA Iwa 7 degree of freedom robotic arm. For the gripper, I went with the WSG two-finger gripper, and the projectile in this case was a brick. The system has a few main components. The first of which is a projectile trajectory tracker, which allows us to determine the exact position of the projectile at any given moment in time. This gets passed to the grasp pose module, which identifies when the projectile has entered reachable space and also how to grab it. Following this is the robot trajectory module, which takes in the locations for the pre-grasp and grasp pose and generates end effector trajectories to get from the initial pose to the pre-grasp pose and then finally to the grasp pose. The last step in the process is to generate a joint trajectory via Inverse Kinematic Optimization, which takes in an end effector trajectory and turns it into joint trajectories for the robot. Projectile tracking is obviously a very important part of catching, but perception systems for this task can be time-consuming to implement. Instead of using a perception system, I relied on ground truth trajectories calculated by a simple projectile motion model without drag. This equation can extract the exact position of a projectile at any given time, which is vital for the next system. The grasp pose module is responsible for taking in the projectile trajectory and finding the time and place to catch it. To find when the projectile first gets near enough to the robot, I use a linear optimization where I minimize the decision variable t while constraining the projectile to stay within reach of the robot. This effectively finds the earliest time where we could possibly grab the object. By instead maximizing t with the same constraints, we can instead find the exit time of the projectile, which is the last possible moment where we could catch it. Now that we have the time of entry for the projectile, and since we know that the projectile has a constant orientation and geometry, we can calculate a comfortable pre-grasp pose for the object. A comfortable pre-grasp pose is one where the gripper is always facing away from the robot, so as to maximize range and movement capabilities while catching. The gripper trajectory module calculates a full end effector trajectory from initial pose to final grasp pose. Phase 1 is the transition from initial configuration to pre-grasp pose, which was calculated by the previous module. For the position component, I linearly interpolate from start to pre-grasp, as there is no obstacles to avoid. For the orientation, I used a quaternion slurp to avoid gimbal lock and find a smooth trajectory. Phase 2 is the transition from pre-grasp to grasp pose, where we must track the projectile's motion while moving closer in order to grab the object. The position component can be determined by the physics equation from the first module, with an additional offset as the gripper moves closer to the projectile. The orientation at this point is constant because there's no rotation in the object. The final module is responsible for translating the end effector trajectory into an executable joint trajectory to send to the robot. The approach used in this system is to solve an inverse kinematic optimization problem, which attempts to minimize the distance between the current joint configuration and a preset nominal configuration, while constraining motion to follow the end effector trajectory. When forming the bounds for this optimization, I was more lenient with the upper bound of the z component, as projectiles normally came from above. Now we can observe the full system at work. Thanks for watching, and I hope you found it interesting.